You knew that?
Yeah.
Why didn't you ask? Okay, that's all right. We got to clarify.
David.
I want to. Yes. Oh, this is Edip. Edip is a fundamental part of this school. He writes books. You just finished one not too long ago, right?
And teach.
Ask him, and he teaches philosophy at a college here in town, and he keeps himself very busy. Okay. Now you'll have to ask Edip because you may see him around. Yeah, it's kind of an open door.
I want you just to feel normal as you are. Just participate, learn. I want to see how you are doing. I used to teach here too when my kids were here. I had 2 children here, 2 boys.
And now he's got one that's graduated and one that's at Princeton.
One finished law school just this semester. The other is finished second year at Princeton University.
You probably know his son. His son is?
Edip Yuksel. Oh, you know Metin?
Of course, everybody.
I played frisbee with him.
Oh, great. Yeah, he's ultimate frisbee.
All right, I'm going to move right here.
Okay.
Put it back. You're responsible for getting this back. I want to go over this 150 very quickly, but I want to do it on the basis of what you know, or what you don't know. Yes?
I already have one note. I just need 33.
33, you just want the answers? Can we just give the answers to it? You got to come up with a specific question. Now you can get these answers, but you remember you have to understand the concepts. We went over some of these yesterday. What's 33? Nobody has it? You have your test.
What's the
Somebody read it for me. Go ahead. You did a great job yesterday. Read the question on 33.
The temperature at which the solid and liquid phase of a substance are
Boiling point. So it is when it can exist as both a gas and as a
Solid.
liquid. All right. Are there any other specific questions? Make sure you have the right ones when you get home. Yes. Before you go home. Yes. 23. Give me a question. Rephrase the question. 23, 24. Do you want to know which number came after 23? 24. That's what you wanted to answer? Okay. Read the question. Can you read it loudly? Her voice is kind of low. She does a great job, but who's got a great voice?
Number 23 or 24?
23, it was 23, wasn't it? Okay.
Okay, the transition of a substance from a solid phase to a gaseous phase without transition to a liquid phase.
Oh, that's supposed to be from. The transition of a substance from a solid phase to a gaseous phase without going through the liquid phase. How many people know? Most people. If you go from a solid to a gas, what is it? Is that right?
Yes.
Yeah. Give me examples of things that sublimate.
Glacier.
A glacier in mountains, right? It'll go from a solid to a gas. Give me another example. Got the carbon dioxide stuff. Go ahead. Dry ice is a very good example where you can see it go from a solid.
I like touching dry ice.
Virtually all materials, all solids will go through sublimation, but sometimes it is so slow that it can take 5 universes for it to disappear. All right, so what I want to do is any other burning questions? We know why it sublimates. We talked about kinetic energy within both solids and liquids and gases. Remember that? We talked, yes? We talked about the cue ball effect, yes?
162.
Okay. You want question ones? Oh, questions on 162. I want to stay on some other things right now. I want to do just a little review. Remember, one of the things that we're talking about in this class and doing this class is we're trying to help you develop soft skills and some metacognitive skills. So some of that you need to be in control of. If you lay your head down on the table, will you do it as well?
No.
No. Does your body posture have an effect on your learning?
Yes.
Yes. Absolutely. Now there's some people that it has less effect than on other people. But for virtually all people, your body position does have an effect. So if what you want to do is get the most out of your time, you're probably going to take a learning position that's a little like this. Are you going to take one that's like this? Oh, now, okay. So you got your learning position, eyes are forward, this is good. Does a hand on the head help you?
No.
I know it feels good and it's relaxing. And I know that some of these things that you do just out of habit, like self-stimming, they're self-stimulating behaviors, like wiggling your pencil, and multitasking behaviors get in the way of your learning. And sometimes you just do it automatically without thinking about it. And what I want you to do is try to control that. I may give you a little feedback as to how you're doing it. We also talked about reciprocal shaping, right? You're doing a good job of reciprocal shaping. It's how we talked about the learner being kind of programmed to learn from a teacher, and a teacher being programmed to teach. We are all teachers and we are all learners. But when we get a lot out, your teacher will get a lot out of you actually learning. And even if you fake it and you look like you're learning, you're going to make your teacher a better teacher. The better the teacher becomes, the better learner you become. The reciprocal shaping. We'll talk a little more about it. Okay, we talked about matter. What is matter? Those are states of matter. He did 3 states of matter. No, give me another state of matter.
Oh, Bose-Einstein condensate.
The one that comes before that relative to, let's do it in the order of the amount of energy contained in it. We're talking about, so it's
Solid.
right? Okay, so solid,
Gas.
Condensate.
oh, guess what?
What's the next one?
Comes on the other end. Okay, so we get superconductivity with it, you remember a little bit of that. So if we talk...
Which one is most abundant in the universe so far?
Pardon?
Visible universe. Which one is most abundant?
Carbon.
Hydrogen.
No, I mean these forms. Water, solid, gas,
Yes.
plasma, and what else? Yeah.
Solid.
Plasma?
Plasma. Now, of course, if we want to talk about dark matter,
Yeah.
which we haven't really talked about, we haven't talked about dark matter or dark energy, we will eventually do that. Then that changes the percentages. Okay, so let's take a look at an atom. An atom is, what is an atom?
Things that make up molecules.
Huh? What?
They make up molecules.
Atoms indeed do combine to make up molecules.
Molecules.
So obviously, what's larger, atoms or molecules?
Molecules.
Molecules. Maybe. Is this a molecule?
No.
Is that a molecule?
Yes.
Yes, that's a molecule. Is it larger than that?
Yeah,
Let's
no.
say, is it more massive than that?
No.
Yeah, no.
No. So we can talk about atoms as far as volume, the amount that the space that they take up, or mass. of course. We know why this is more massive. Why?
Because it has more neutrons or protons.
And the mass in an atom is contained where?
In the
The
nucleus.
nucleus.
Most of it, the electron does have a certain amount of mass, but it is a negligible. Is this helping you? You're supposed to be doing your part. This, you look really good, incidentally. So, if we're talking about if we have an element maintains its properties. If we have 1,000 of these, or 10,000, or 10 million of them, they retain their property all the way down to, now I'm going to say this with some hesitation, but your book will say this, all down to a single atom. Single atoms actually behave differently than bunches of atoms. But for the most part, we say it maintains its chemical properties. And what influences an atom's chemical properties? Its property to combine with other atoms.
Electrons.
Electrons, where? Which electrons?
The ones in the outer shell.
The ones in the outer shell, and we call those electrons valence electrons. And a measure of how much they interact is called valence. They're valence electrons, the amount that they interact is called valence. It's a measure of the amount that they interact. Did I lose the eraser again? Okay, so we're talking about now, we got all the way down to the atom. Atom itself means uncuttable, but can it be broken down?
Yes.
Yes, it can be broken down into what?
Quarks.
Let's break it down, not quite that far.
Protons and neutrons.
Okay, so this is the protons, neutrons in the nucleus. Now, of course, I'm going to use a planetary model for this.
Yeah, and those are the electrons.
And these are electrons, and this is charges, negative,
Positive,
neutral, and that's neutral. All right, and the overall atom is it neutral? Is it positive? Is it negative? Neutral. If we're talking about an atom itself isn't neutral. What if I have that? Is that neutral?
That's a positive.
Yes, and it's called an?
Positron.
It is called an?
Or an ion.
Ion.
Positrons are antimatter.
Okay, give me the positron here is
Positive.
positive. And this is just the antiparticle for this, and this is the antiparticle for this. And if they come together, then they're going to annihilate. And
Cause a lot of energy.
we can actually guess how much energy will be released with the mass energy formula, that famous mass energy formula.
E equals MC squared.
E equals mc squared. What does this stand for?
Energy, mass, light, the speed of light squared.
Speed of light. Very good. So this is a huge number. A little bit of mass means a lot of energy. This also must mean we can take mass, right? Transform this formula for me.
E equals over, E over C squared.
Okay, is it E over?
E squared times C squared by 2.
What?
C squared.
Okay. So we can see here that we can convert energy to mass and mass to energy, right? So let's take a look at this. We call this a nucleus, and we call those two things inside
Nucleons.
nucleons. Okay. Let's see. We did this, right? AZ notation. So in this, the A represents what?
Atomic mass.
Okay, atomic mass, and atomic mass is calculated by the what?
Neutrons, amount of neutrons.
Okay, the amount of neutrons? The amount of protons.
Oh, but isn't, no, I thought it was neutrons.
Okay, you think, how many people think you calculate atomic mass on the basis of protons?
Oh yeah. No, that's the atomic number. The
Yeah, that's the
atomic
atomic
mass
number.
is
That's
the
how much
protons
is that?
and the
Yeah, that's how it
neutrons
gets
added
to-
together.
Right, so it's both the protons and the neutrons added together. This one, Z represents
number.
atomic number, okay? And if you have the atomic number, do you need this?
No.
No, so sometimes you
Because
just
it
see
represents.
it, sometimes you just see it like this. So lithium, what is the element symbol?
Li 3. Number
Li,
Number 3.
and it is,
3.
okay, it says, it would be 3, right? And, well, we ought to put up a chart here. Let's do this. Now, most of this is review for you.
3 points off.
We took hydrogen. We looked at this. It had really, it was what goes here?
2.
2.
Hydrogen.
No, 1.
One.
Sorry.
And what goes here?
Helium. 2.
1.
2.
Why?
Because it's
Yeah, because
Yes.
its mass is 1.
If there's only
Okay,
that means
so
there's no neutrons, so
this.
it's just protons.
Yeah, I forgot. Yeah.
I can't see anything, David.
That's the same thing.
This is this the same thing?
No. Yeah.
Now, what did we call this?
isotope.
It isn't. Very good. It's an isotope.
Yeah.
Me.
Who said isotope? What's isotope?
It's more neutrons than electrons and protons.
Okay. So this has more
Neutrons.
neutrons. So this has 0 neutrons.
That has.
This has
One.
1 neutron, and we call this
Hydrogen.
Deuterium.
started with deuterium. Very good.
Oh.
And this one we call
Tritium.
we're adding excess neutrons. What would you expect to happen with tritium?
It's more unstable.
It is more unstable, which means it's going to become
Radioactive.
radioactive. Excellent. Okay, so we had, I lost my sheets here. Oh, there they are. So did we give this isotope a name?
It's protium.
Yeah.
Yes, very good. So this isotope is
Protium.
tritium. And one of those happens to be radioactive. Which one? Tritium. And we can predict when atoms are going to be radioactive based on the number of neutrons they have. We call these excess neutrons. So if we have more neutrons than, more or less neutrons than protons, then it is more likely to be radioactive. All elements above what happen to be radioactive?
Above lead.
Above lead.
Yeah.
Anybody know what the symbol for lead is?
PB.
Okay, and anybody know the atomic number?
82.
92.
It's 82.
96, 46,
It's
92.
92 is uranium, I believe, correct?
Yeah, no, 82 is the atomic number.
It's 46.
Oh, for uranium? Yeah, uranium is 92. PB is 82.
Uranium is 90.
82.
Yeah. 82?
Yeah, it's 82.
Well,
82?
And look, it's 82.
Let's look at the
Wait, I
chart.
got the book!
No.
Come on.
I swear it's 82.
That's $20.
82.
Dang it, it is 82.
Yeah, what did it take? So
Okay, oh. You see this, you see at the top, this is a different, but a very standard display. This is the, I got it. This is this number down here. That's the atomic number. This is the atomic mass. Why is that not? We don't get partial neutrons. Why does this have a number that's not a whole number?
You subtracted
Yeah.
the protons.
The protons
That's
from
the
the
charge.
No,
neutron.
well, we can subtract this from this, but shouldn't this, if this is atomic mass, shouldn't it be a whole number?
No.
Why? Why?
Because of the charge.
Someone said isotope here.
It
Who said
has to do with the isotope.
Yeah.
That is, that all three of these occur, and naturally. However, this one at a very low rate, this one at a little higher
And
rate,
that was the highest grade.
and this one is the most common. So, if we look at hydrogen in here, if I can find hydrogen, it's hiding from me, we see that hydrogen doesn't have a whole number here. It's just a little bit larger.
Yeah, it's interesting.
And somebody tell me why. We talked about this.
Those are
Because they are average atomic masses. So you take all of these and you average them in the naturally occurring element. We didn't talk about this. Naturally occurring elements, now some people argue about this, include all of the elements below, below
Proton.
92, which is
uranium.
uranium.
Wait, David, I have a question.
Yeah.
Yes.
The element that comes 93, that comes afterwards, I forgot what it is. It's
Plutonium.
whatever. That one has less neutrons. That has a less weight than uranium.
Okay, good point.
It has 237, and then uranium has 237.
Anybody know why? Why does it have less weight? It's not because it's decaying,
That's radioactive.
not because it's radioactive.
Or is it because those two are all occurring in its own
That's
scale?
the average
Because it's on
mass.
the H3.
Does it have something to do with
Is there any rule, there happens to be a rule here, but we're not going to cover it. Is there any law that all elements must have about the same neutrons? No. Why do you think that a higher element on the periodic chart would have a higher weight
Because it has more protons.
or less weight? Not protons.
Neutrons.
Neutrons. Neutrons relative to protons in mass. Are they exactly the same?
No.
No.
No. Which one's larger?
Uranium.
Which one's larger? Neutron or more massy?
Oh.
Neutron or electron?
Neutron. Or proton.
Neutron.
Neutron. You're right. Now we talked about things. Let's take this a little further here. We got protons and neutrons. Is this an elemental particle? What does elemental particle mean? When I say, what does elemental particle mean? It means, what is an elemental particle?
Hold on, I got this.
Elemental particle.
It's
the beginning. It is actually the very beginning. You can't cut it any further, or it is not composed of smaller units. It's the beginning. It is at its fundamental level. We used to think that protons and neutrons were elemental materials. We used to think that atoms, now this is a little weird, atoms happen to be elemental. We're called elements, right? Yeah. Atoms we can't cut. Well, atoms are not elemental particles.
We can cut
We can't actually make them,
Smaller.
they are composed of
protons, neutrons.
smaller objects. Now, we talked about how some of this works. Now, if we look at this, the distance between here and here relative to the size, the volume of this, is the volume of all of this stuff inside of an atom, relative to the size of the proton, neutron, electron. Is it large, small?
Large.
Very, very large. This is almost insignificant. Now, all of these have wave properties. If we talk about this in field theory, and I touched this, but we didn't touch it much. We can look at these particles giving rise to what we would call matter, but they may in fact only be fields. If this is a magnet, this is the north, this is the south. A magnet produces a field. If I take two magnets, and one with the north and the south, and I put them together, and I get them to a certain distance, what happens with them?
They push against, they resist, they attract.
Depends on
They're
which sides you
opposite,
have
it
together.
depends on the poles.
Yeah.
If they're
Because
different
opposites
poles,
attract. And if you have south and
so
south, they'll attract.
you can feel it really come in. Now we'll do this little experiment. We'll put some iron grain, but we can actually see the fields. We can measure the field. So if we think of these as having fields, when we get down to the subatomic particles and into the particles that they're made of, then it is as no mass is itself created by fields, not by tangible objects. We're used to tangible objects here. Okay, so protons. What are they composed of?
Quarks.
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 So quarks. What kind? We talked about a few types of quarks.
C quarks.
Up quarks, down quarks,
Up,
drain
up.
quarks, top quarks, bottom quarks.
Up, down, up quarks, down quarks,
Drain
Arm.
top quarks, bottom quarks.
Yeah.
Okay. And a neutron is made of
Two down, one up.
two
One.
down, one up. And protons are made
Two
of,
up and one down.
okay, two up
One down.
and one down. Okay, good. So we talked about fermions. Right? We talked about fermions?
Yeah.
Are you with us?
Fermions
This will
relate to
always
the
be hard if you don't come with
Pauli
it.
exclusion principle.
You guys and gals are doing a great job. This is a good review. You've got very good recall on this. So, fermions. Everybody remember
They
what a
relate to
fermion?
the Pauli exclusion principle and they give rise to matter.
Yeah. Good, you got your notes. They obey the Pauli exclusion principle. They occupy space. So fermions represent what? Matter themselves. Now, we talked about bosons, right? And bosons, do they,
don't follow.
okay, do they follow the Pauli exclusion principle?
No.
Okay. We talked a little bit about the Higgs. Where, does anybody remember where most of the mass comes from? You know, most of the mass is located in an atom in the
Nucleus.
nucleus. And the Higgs is thought of as containing mass, but most of the mass in an atom doesn't come from the nucleus. Where does it, or it doesn't come from the, it's in the nucleus, but it doesn't come from the Higgs. It is generated by what?
The electromagnetic radius.
Gauge
Bosons.
bosons. Okay, very good. Gauge bosons are
The force carriers.
the force carriers. And we talked about 4. Did we talk about 4 gauge bosons?
Yeah, well, technically 5, but yeah, because Higgs.
Yes,
boson
you're
is-
correct.
yeah.
Technically 5. Okay.
Photons, W and Z bosons.
Okay, so
Gravitons.
photons.
W and Z.
W
Okay,
and Z.
photons travel through space at the speed of light. So that suggests their mass is
The electromagnetic carriers.
0. I remember what it takes to accelerate mass to the speed of light is probably more energy than there is in the universe. So in order for a thing to really not approach, but travel at the speed of light, it is inferred that its mass is 0. Electrons have a low mass, and, well, let's see. They are charged particles, but, okay, so what other types of energy carriers or
W and Z
gauge bosons? W,
And
and we
Z.
didn't talk about these too much. Z bosons, what else?
Gravitons. And gluons.
And gluons.
They're just gluons.
And what else?
Gravitons.
Gravity.
Which technically they haven't found any yet.
I input enough energy, and I'm taking 2 atoms of hydrogen. We end up with
Helium.
helium. Is that nuclear? Is that nuclear decay, or is it
Yes, nuclear genesis.
is it nuclear synthesis? Synthesis. We're making more elements. Before we do this,
It's
what
building heavier
determines the difference between elements? What's the
The number of
determinant?
protons.
The number of protons,
in the
not the
nucleus.
number of electrons.
Yeah, that doesn't matter.
So protons is really what determines the
The element.
Neutrons
Determine the mass of the element.
determine
Mass.
the mass, yes, but what else?
Oh,
Iso means the same, and
So,
taupe,
means
Wait,
the same number of protons, different
different
number of neutrons.
same number of protons, different
Isotone
number
is the same
of
Neutrons.
neutrons.
Isobar is the
And
same.
isotone,
It's the same
Same
mass.
number of neutrons, different number of protons.
so the same number of
Different number of
neutrons
protons.
and different number of
Protons.
protons.
And
Are
isobar.
isotones the same element?
No.
No. And, okay, and what is an isomer?
Isomer.
No, it's
Same number of neutrons and same number.
excitivity and different number of protons and
Okay, there's another one
Yeah.
too.
isomer.
Isobar.
Isobar.
It's the same.
Same mass.
So an isobar, bar means weight, really we mean mass by it.
Same
But iso the same, so it will have the same atomic number. 2 elements with different elements with the same atomic number.
Cannot be.
Okay,
Can
now,
it be, David?
huh?
Can it be? Atomic number is proton, if this the same element.
No, atomic number is protons plus
No, that's
neutrons.
Oh, it is atomic weight, you mean?
I mean atomic weight,
Yes.
did I say atomic
Okay,
weight?
yeah. Okay.
Yeah, nobody caught that.
Isobar.
So it's the same atomic
I was there.
mass, but
Different.
different elements. Right? That means it'll have the same atomic mass, but the different atomic numbers. Right? Okay, so we got this. Now we have isomer.
Oh, it's the same number of protons.
That's the same number.
But different level of excitivity.
Okay, same number of protons,
And
same number of neutrons, and-
Different number of
Different number of
excitivity.
and different level of exciticity of what part of the atom?
The nucleus.
The nucleus. Now usually we talk about excitation of the electrons.
Yeah, that's the outer shell.
Okay, so let's see if we, oh, we got another one there. We got isotopes.
Isobar.
Isotropic?
Uh,
Is it isotropic?
how about, isotropic means what? Same in all directions.
Yeah.
Let's see. When we ionize, when we strip off an electron, if we remove an electron, it changes the what? Changes the charge, and we call it an ion. Now we let's see. Oh, we haven't talked about decay. We were talking about these in nucleosynthesis and nucleogenesis and nuclear decay. Which one is this?
This is nucleosynthesis.
And where does this occur?
This occurs in the nucleus.
It does occur in the nucleus, but where do we see this going on every day? In the sun.
Oh, yeah.
So the energy comes from this. What do we, oh, we're missing an important person. Oh, Logan, let's let you do this. Logan, what do we call this? When we're taking an element, inputting a great deal of force, kind of storing it, the energy in it, we call it what?
Oh, nucleosynthesis.
We call it, it starts with an F.
Oh, wait. What?
Fusion. So what is it? Fusion. And what is fusion? Okay, and we create heavier elements, if you like to think of it that way, or not necessarily heavier because they could have different
Charges?
numbers of neutrons, so they could have different masses.
Activity.
So, and the other one that we talk about is fission. And what is fission?
It's when they separate.
When we break it down into smaller elements. Now, I say that with a little bit of hesitance, and even fusion and fission. But usually in fusion, we're building the elements up, we're adding more protons, and in fission, we're breaking it down. Can we do that? Can we have a sustained reaction in all materials?
Good pressure, guys.
So it's alpha, beta,
Something like that, right?
And gamma.
and
Got
gamma. Right?
I'm not like Leonardo da Vinci, but
Well, you should have started
Okay.
gamma.
Who has gamma?
Me.
I don't know.
Go ahead.
I know what gamma is.
All of them are pretty different.
That's on.
No.
Oh, no, that's
Oh, is that gamma?
I think that's
It's
an
more
R.
like
What
an
is
R.
that?
What's that?
Yeah, well,
That's an
it's a
R.
poorly drawn gamma.
That's an R.
Oh,
It's like
you don't-
a weird Y.
You don't like it, huh?
If my alpha's better.
So let me see if I can do it better.
Guy started with.
That's better. That's
Yes.
gamma.
That looks like
Okay.
a Y.
Yeah. Wait, doesn't
That
the
looks
alpha look like a
like
fish?
the islands in
A little
Hawaii.
bit. I was using something that
Yeah. That's a lot better.
that's all right. So
Sorry, I'm not.
relative to its ability to do harm to a human body.
Our body produces alpha, but
Oh.
not beta or gamma.
Okay, so would we do it in that order?
What?
Alpha,
Alpha,
beta,
beta.
gamma.
Yeah, that's the right way. But like, you should draw them on top of each other.
I like gamma radiation.
Alpha should be on top of beta. And
Except the
Okay,
Bravo
so
looks
alpha comes first,
Yeah, beta.
beta,
And then
and gamma. All right.
What the heck is
Now,
that?
guys, who knows? It's something.
There are a number.
Let's say we have a neutron. Here's our little neutron, and somehow we get it into outside of the nucleus. Is a neutron going to survive very long?
No.
Are you with us?
So that's like 8 minutes.
What keeps the particles together in the nucleus?
Strong form?
What is the force? Yes, it's the strong force that keeps the proton